Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always it is an honor and a privilege to be serving you here today as it is every day here in my virtual classroom. Step on aside as we jump into the section 7.1 to 7.3 quiz review in the Big Ideas Math Integrated Math 3 textbook. We're dealing with things regarding sequences and series. I think the first section is really just anything regarding sequences and series, and then 7.2 is arithmetic, and 7.3 was geometric and their specific natures. Now in 7.1, I remembered saying the phrases arithmetic and geometric sequence, and probably not series at the time, but I used the formulas then, so it's fair game for me to say if we're doing the review part here, anything that resembles arithmetic, I'm just going to mention as arithmetic with no second thought as to what section it's in, even if it highlights section 7.1, and same thing with geometric for section 7.1 stuff. If it's there, I'm using it. And I don't know how much they're going to cover series. We have 19 questions to cover here. Jump to the description section down below if you want to find the PDF of this single page, as well as any graph paper I use. I did use the scaled graph paper for arithmetic at the time, and the taller ones for geometric, so if I think it's fair game for me to use one versus the other, I will, and then if I do, I will attach both. Find the timestamps for each individual problem if you'd like to. Without further ado, I'm going to go ahead and get started. We are going to, numbers 1 through 3, describe the pattern, write the next term, and write a rule for the nth term of the sequence. And like I said, this is out of section 7.1, but that doesn't negate the fact that if something's arithmetic, I'm going to call it that. When they say describe the pattern, that's how I've been describing it. If it's been arithmetic, I've been calling it arithmetic, and that's what number 1 looks like. It has a common difference of 6. You add 6 from one term to the next. That is what an arithmetic sequence does, and that's how I'm going to describe it. So this looks arithmetic to moi, with a constant difference. Write the next term. The next term would be adding 6 from here. So what I'm going to call a sub 5, the value of the fifth term is 19 plus 6, which would be 25. And that's how you find the value of the next term. Just continue whatever pattern is going on there. Write a rule for the nth term of the sequence. This is where to find any a sub n, the value of the nth term. What you can really do in this, listen, there's a rule for it, the equation we've been writing, but you start from the first term and you add your common difference n minus 1 times. If I want to find the fifth term, I add my common difference 4 times. 1, 2, 3, and 4. And that's where you get that here. So this is an example of the rule you can write. You've been seeing arithmetic sequences simplifying this rule, however, by distributing the 6, for example, like that, and then combining like terms, you get 6n minus 5. So there is the nth term rule for this arithmetic sequence. For whatever reason, 7.1, I gotta ask the bookmakers what they were doing with it, introducing arithmetic sequences in 7.2, yet using questions of arithmetic in 7.1. I don't know. Number 2. Number 2 is this interesting case. We did run into these in 7.1, and I don't know what to call them. It says describe the pattern. Listen, I can describe the pattern still. I just can't give it one of the names because I don't know it. It's arithmetic in the way that it looks like the value, the absolute value adds 5 each time. 5 plus 5 is 10, plus 5 is 15, plus 5 is 20. But Mr. Robinson, these are negative. I know. I'm just saying that I can tell the next number, which we're going to get to. Let's start with that. Next term is going to be negative 25, because 20 plus 5 is that, and then you make it negative. The ones that end in 5, the every other term is negative. And that's where it's kind of geometric, right? Because geometric sequences, you can multiply by a negative number each time and the signs will change, but this isn't the same number over and over. So it's not a constant common difference truly, because we're adding 15 and then subtracting 25 and then adding 35 and then subtracting 45. But it's not geometric either because no common ratio. So, I mean, what can we say here? Signs alternate. You know, I don't think I described these in the 7.1 when we actually did it, but signs alternate and absolute value increases by 5 each time. By 5. That from one term to the next. Therefore, that's where we're getting the negative 25 from. They do say write a rule for the nth term of this sequence, and I believe this is something I could do at the time. It's a little bit interesting because it combines arithmetic. Like I said, it combines arithmetic with geometric. It has that. How do I say it? It has the lore of doing this, like an arithmetic sequence would. Start from the first term and add 5 each time to it, in tandem with multiplying by a negative number each time for the signs to change. In this case, multiplying by negative 1 each time. Now, I don't just want to multiply by negative 1 once, because then it's going to make every term negative. I want to multiply by negative 1 in such a way that for the odd terms, it'll be negative, and for the even terms, it'll be positive. The best way to do it to me is raising it to the nth power, in that the first term would be raised to the first power, and raising a negative number to an odd power would make it negative, and raising it to an even power would make it positive. It would become positive 1. So it has this thing in mind right here. Now, if I simplify this, all this changes into just 5n. 5n minus 5 plus 5 is just 5n. So this just becomes 5n, and that 5n multiplies by negative 1 to the nth power. That's how we'll leave that. And that negative 1 does have to be in parentheses, by the way. So that's my appearance for that one. That's what I'm doing with it. I believe in that sequence. I don't know how to state that rule, but we'll go with it there. Let's go to number 3. And yeah, I haven't seen these problems before, so I'm digging into it the same way that you are here. These have something interesting as well, in that I don't believe this... I have to look into it. I don't believe that this is arithmetic or geometric either. You can say, but Mr. Robinson, the top is adding 1 and the bottom is adding 10. That's great that the top's adding 1, but if the bottom's adding 10, that's not how, this isn't plus 1/10. You need a common denominator to figure that thing out and what this will be. I'm also, I'm curious about the reduced fraction form in these things. I don't think it's very helpful for us to use it. This would reduce to, for example, 1/15. Don't keep that, by the way. And this would reduce to 2/25. I don't see anything in that nature that's going to contribute and help us either. With this constant common difference in the denominator, there's nothing that's going to make that arithmetic, folks. That's not an arithmetic sequence. You can test it. You can do this minus this and then this minus this and see what you're getting as a result of it, but that's not what's happening. Are we adding 1 on top? Sure. Are we adding 10 on bottom? Sure. Is that mathematically saying that we're adding 1/10? No, it's not. So the pattern is clear as day regarding I can predict the next term. Oh, the rule. Okay, we'll talk about the rule in a second. I was going to say the rule is going to be tricky. I was thinking too hard about that. Okay, so add 1 to the numerator and 10 to the denominator. That's clear as day, right? Maybe that's why 7-1 didn't have a lot of arithmetic and geometric like they foretold. They're like, guys, this is why I didn't talk about them. We want to do any sequence of any type. Now, a sub 5, the next term in this set will be adding 1 to the top and 10 to the bottom. So 5 on top, 10 on bottom. 60 on bottom would be that. They are not reducing fractions, but if we did, this would be 1/12. Now, they want a rule. Don't think too much in terms of arithmetic and geometric, just like the last one, although the last one was both arithmetic and geometric kind of together. A sub n, the first term, has a 1 in it. The second term has a 2 in it. Third term has a 3. Fourth term has a 4. Clearly, the n is on top there. Substitute n for that, and that's what we get. A sub 5 has a 5, right? Now, this term seems to be, it's 10 times bigger than the number after. 3, 34, 45, 50, things like that. So if we multiply n by 10, if I did 10n, then that would give me 1 over 10 and 2 over 20. I need to make this an n plus 1, if you will. And we could distribute the 10 if you wanted to. I kind of like it more like this, where you're making that n 1 larger than it is before you multiply it by 10. So taking a look at this, here's how it would work. A sub 1 is 1 over 10 times 1 plus 1. That's 1 over 10 times 2, 1 over 20. And then 2 over 2 plus 1 is 3 times 10 is 30. So this does work as a rule. Neither arithmetic nor geometric, just some other thing. And it works out. I'll take it. All right. As I might have over-explained those ones, they work for me. Let's go to numbers 4 through 6. Write the series using summation notation, then find the sum of the series. So this is still part of section 7.1. We did introduce series here. We just didn't talk arithmetic and geometric series with their formulas. So summation, and these were, okay, I do remember now. Okay, so summation notation is the concept where we are going from the first term to the last term, and given it has a constant difference of 1, that is 15 terms in total. Clearly, whatever you're substituting in for I, and that's a temporary variable in place of n, whatever substituting for I is the value that's there. When I is 1, the value is 1. When I is 2, the value is 2, straight up. And summation notation says take the next term and add it to the terms before. So this is what it looks like. Now, a formula that they gave us, and I don't ever remember it, but the formula to keep in mind here, from 1 to n of I don't remember what letters they use. Actually, they don't. I don't remember if that's how they write it, but it is n times n plus 1 over 2. You know, honestly, I should look this thing up. I think it's n times n plus 1 over 2. Yeah. And so we're going to be doing that here. So in this way, they say find the sum. Instead of literally doing those things added together, we're going to be getting here, n is 15 in this case. So 15 times, and then 15 plus 1 is 16, divided by 2. 15 times 16 is 240, and 240 divided by 2 is 120. Okay, so that's what we get. Hold on, my computer's making this kind of loud buzzing thing. I think a fan is pushing against the shell. Let me try and take care of that right now. Give me 1 second. Okay, I believe I addressed the humming. All right. We finished 4. Number 5. Wait, you write the series. I'm sorry. Write the series using some ancient notation. Okay, so on number 5, we have 0 plus, okay. 0 plus anything will just be that something. I don't know if I have a shorthand version. See, the last question was very specific to the sum of the first 15 positive integers. And that has kind of a formula thing within it. There's reasons to that. This doesn't necessarily have any of those natures with formula. I think if we do these, we actually got to add up what these are. I'm just going to say that. Now, when it comes to a summation notation set, we're still going to use sigma. Let's go from the first term. How many terms would this be? 1, 2. Oh, by the way, 0 could be represented as 0 over 1 to feel that pattern out, if you notice there. Because, yeah, I might want to do that. So 0 over 1. So that's the first term, and that, I guess it goes to the 8th term. So from 1 to 8. Of the bottom would be that I we're plugging in, right? So I would be down here, and this is 1 less than that. So I'm going to say I minus 1. Yeah, there's no formula thing that I'm aware of with this. For us to do the sum, we're going to have to add them up together. And to do it best, get a common denominator. Now, it's going to take a moment for me here. Let's keep writing what the rest of them would be. I'm going to ignore the 0 outright. I got 1/2, 2/3. I'm going to try and pair things up the best I can, or see if there's a common denominator that's very easy to come up with this 5/6, 6/7. And if there's a faster way to do this, I apologize. I didn't seek it out. You know what would be interesting to do? I'm going to find the least common denominator of all of them by breaking each number up into their primes. Now, 2 is just the number 2, and 3 is 3. 4 is 2 times 2. 5 is 5. 6 is 2 times 3. 7 is 7. 8 is 2 times 2 times 2. What you'd have to do is find everything that's missing in the other terms for this to work out. For example, this 2 is missing a couple other 2s that this guy has. A 7, a 3. Oh, this might take a while, guys. A 3, and a 5. So I got to multiply this thing by 5, 3, 7, 2, and 2. I'm going to find the least common multiple, that common denominator for all these things, and see what's missing. The 3 is missing a bunch of 2s and a 5 and a 7. These 2s are missing a 2. Remember, we're missing what another guy's got. It's missing that 2. You got to break it up into all the primes, right? It's missing a 2, a 3, a 5, and a 7. This 5 is missing all 3 2s here. And I don't even know what these numbers are yet. That's the real problem. 3 and a 7. This 2 and 3 is missing a 5, a 7, and another 2. And is that it? 2, 5, 7. I think so. 7's missing 3 2s and a 3 and a 5. And these 2s are missing 3, 5, and 7. Okay, I feel like it might be missing somewhere. 1, 2, 3, 4, 5 numbers. 1, 2, 3, 4, 5. Oh, I'm missing another 2 here. Okay. All right, so let's figure these things out. Sorry about this. Oh, they all multiply to the same number. Duh. But we have to multiply those on top. I think that's the point, that what I have to do here, right? So when I multiply that on top and bottom with these things, oh, this might take a moment. 15 times 4 is 60, times 7 is 420. So this is 420 over, I guess that's 840, right? Over 840. And then 2 times, hold on. I have to, there's a faster way for me to do this. I just don't know what it is. 2, 4, 6, 8, besides a calculator. 2, 4, 6, 8. 2, 4, 8, 16, 80, 560. Anyway, goal here is common denominator. You can let your calculator, if you go to the calculator and you type these things, it'll work it out. I'm trying to go calculator free. 4, 8, 24. Move on if you don't want to listen to what I'm saying. 120 and 840. Wait, that can't be 840 over 840. 2, 8, 24, 120, 840. Oh, I'm sorry. That's the denominator. That's the denominator. 3 times 6, 18, 90, 630. 630 over 840. I'm suddenly realizing I might have faster ways to do this if I know how these things work. Like, for example, 6/7. I know 6/7 of 840 would be 720 over 840. I'm thinking of the fractions in my head now. That might be faster. Anyway, 4 times 8 is 32, times 3 is 96, times 7 is 672. I might be wrong there. Let me do that one on the calculator at least. 8 times. That was right, 672. 5 times 25, 75, well, 175 times 4. Oh, let me do that again. 25 times 4 is 100, 700. 700 over 840. 6/7. What did I say? 720 over 840. And then 7/8. Okay, 8 times 3, 20, 45. Oh, 7. 7 times 49. What's the fastest way to do that? 49 times 15. Is that 735? I'm going to do this one on the calculator. 49 times 15. 735. Okay. Plus 735 over 840. Apologies for all this, by the way. And I am going to use the calculator to add these up probably afterward. This is a longer quiz thing than it has to be, especially if they're like, yeah, guys, just add them up. Okay, let's see. I'm going to use the calculator. 420 plus 560. I'm using conventional versions of what to do, though. I don't know if it was wise to do that. They didn't say. Because they didn't have a formula either. All right, all of these add to 4,437. Interesting kind of like number. Over 840. I would say, I don't know. I would say I'm not sure if they simplify, but you might as well test it. So I'm going to go to the calculator in general here, right? So I went from not using a calculator to, hey, let's just use the calculator. So I got all these to add up to that number. If I divide it by 840, I mean, the decimal's weird, sure. Does it reduce as a fraction? Yes. They divide by 4, not 4, 280. I don't know what they divide by. But it reduces to 1479 over 280. So that's our sum. Okay, super apologies on the problem in that, yes, could you go in your calculator and type, 1/2 plus 2/3 plus etc. all the way to the thing? Yes. And is that something they want you to do? I don't know. That's why I was presenting the other parts. The other parts I wanted to stave off not using, or using a calculator. I want to confirm I got the right answer. I staved off not using a calculator in hopes that for things, that's the same number there at least, in hopes that if there's something you have to avoid doing, you can practice it. And then I used the calculator where I said, guys, I got to do 49 times 15. Let's just figure it out. Okay, so there's the sum there. This will be the longest quiz review I've done, I suppose, with all this math. Excuse me. Number 6. On number 6, we have 9 plus 16 plus 20. So these are perfect squares. And there's a formula for the sum of the first number, the first whatever squares, perfect squares added together. Now we're missing the first 2 of them, and I'm going to call attention to that as well. Because the formula that we would do from the first to the nth of something squared, if I recall, is going to be n times n plus 1 times 2n plus 1 all over 6. Now, we got to use this. We can't just cut this thing short and put a 3 on this or something like that because, by the way, this is 3 squared. We would have to start from 1 if we're going to use this, and I'm fine with doing that. Knowing that we are not including 1 squared and 2 squared. So we have to subtract these out. We have to subtract out 5 from our result. We're going to add the first 10 squares, some of the first 10 squares, and then subtract 1 squared and 2 squared. So we're going to go from 1 to 10 of I squared and take out basically 1 plus 4. So this is going to be n times n plus 1 times 2n plus 1, that's 2 times 10 plus 1, which is 21, all over 6, minus 5. That result, minus 5. I'm going to reduce what I can here. 21 over 6 can both divide by 3. Here you get 2 and 7. 10 over 2 is 5. So now I can do 5 times 7 times 11, which I believe is 385. So we get 385 minus 5, which is 380. But Mr. Robinson, I could use the calculator and done these ones. No, I know, but these ones actually have a formula within, and I think that's the goal, using these ones in that way. I mean, what if they did it for the first 20 terms? At some point, you're going to want to give, and they helped you by keeping it small, and we can work off that. All right, numbers 7, 8, and 9. Write a rule for the nth term of the sequence. This is sections 7.2 and 7.3. I'm not going to redraw the graphs. What I am going to do is write out the sequence given what they have. N is the position of the term, so 1, 2, 3, and 4, and then these 0.25, etc., they are those values. So I want to write out 0.25, 0.5, 1, wait, 0.75, 1, and 1.25. This is out of one of the sections, arithmetic or geometric. Now we get to be specific about it and write those rules always. In this case, this is an arithmetic sequence given the common difference. They don't ask us to explain why, but you can tell that there's a common difference of 0.25. Now the first term is also 0.25. So in a lot of cases, if you know how to clean this up fast, you can. I'll write the answer shortly after, but the first term is 0.25. Common difference is 0.25 times n minus 1. When you distribute that 0.25 there, you get 0.25 plus 0.25n minus 0.25. I'll be very happy to not have to say 0.25 pretty soon after this point. Subtract the 0.25s right here, and you're left with 0.25n. I no longer have to say 0.25. That's the rule. It is an arithmetic sequence given the common difference, and there's the formula off of it. Number 8 is a geometric sequence, and it's actually our first exclusive geometric sequence that we get to use. So we actually also get to refer to the rule in such a way. We haven't yet spoken on it in this video. So there's a 0.5, not 0.25. And we are doubling each number times 2 each time there. That's a common ratio, as geometric sequences would. Your geometric sequence formula takes the first term and multiplies by your common ratio, n minus 1 times. I say n minus 1 times by multiplication using exponents to the n minus 1 power. So a sub n in this case takes the first term and multiplies by the common ratio n minus 1 times like so. When we had longer problems before, here we have some quicker problems after. Number 9. I think 7.1's the hardest section among these. Actually, I take it back. 7.3 had some weird... If you'd follow the textbook stuff with me, there were some problems at the end of that tested my ability to be the leader that I could be for you. So on this one, a common difference of -2, which means an arithmetic sequence there again as well. I think it's, I didn't write these out before. I should be writing them out. The first term is 1. The common difference is -2. It's an arithmetic sequence. So we're going to say a sub n equals 1 minus 2 times the quantity n minus 1. Oh, my computer's doing that buzzing thing again. Hold on. I kind of just adjusted it. You probably can't hear it. It's really annoying for me. I moved it. There we go. I don't know why it does that. If you know, comment below. Distribute a -2 here. -2 times -1 is a +2. 1 plus 2 is 3. You get -2n plus 3 as a simplified version of what we'd be saying there. Okay. Number 10, 11, and 12. Tell whether the sequence is arithmetic, geometric, or neither. Write a rule for the nth term of the sequence, then find a sub 9. So this sounds a lot like what we were doing in 1 through 3, only they call this section 7.2 and 7.3 because they get to officially use the phrases arithmetic and geometric, although I was kind of using it before. 13, 6, -1, -8 is a subtraction of 7 from one term to the next. That very thing would make this arithmetic. Write a rule, then find a sub 9. Now the rule is going to help us find a sub 9. So doing what we did before, 13 is the first term, -7 is the common difference. If I distribute this, I get -7n plus 7. And 13 plus 7 is 20. You get -7n plus 20. To find the ninth term, we'll substitute 9 into that rule. Now remember, you could substitute. This is an arithmetic sequence rule here, by the way, too. You can use that. But we have this, so we'll use this. So -7 times 9 plus 20 is -63 plus 20, which is -43. The ninth term of the sequence is -43. Done using the rule as opposed to subtracting 7 about 5 more times. Although that would get you there. Number 11, 1/2, 1/3, 1/4, 1/5. I did mention back on number 3, having a constant common difference in the denominator is not a normal math thing to do with respect to pattern. You can tell what comes next. That doesn't mean it's arithmetic or geometric in nature. This is a natural. There's no common difference here. To show you, this number is 0.5. This is 0.3 repeating. This is 0.25, and this is 0.2. Clearly not a common difference. We can tell there's shrinkage, but there's also convergence on this thing as well towards 0, but it's lessening as we go. This is a neither case. Now, if they want you to support the neither case, you'd have to show there's no common difference. Really, you'd have to show that whatever we add here, we don't add here. For example, 1/3 minus 1/2. If we get a common denominator, that would be 2/6 minus 3/6, which is -1/6. That means we're subtracting 1/6 going from this term to this term. And then let's check 1/4 minus 1/3, which you get 12 is the common denominator there. So you get 3/12 minus 4/12, which is -1/12. So we're subtracting 1/12 the next time. Not a common difference. Not arithmetic. As far as geometric, you got to show that you're not multiplying by the same number from one term to the next. So let me change these to blue because I'm going to do green for geometric here. For geometric sequence, we say 1/2 times what is 1/3? You would do 1/3 divided by 1/2. So 1/3 divided by 1/2 is 1/3 times 2/1, which is 2/3. We are multiplying by 2/3, going from one term to the next here. And 1/4 divided by 1/3 is next, which is 1/4 times 3/1, which is 3/4. So we're multiplying by 3/4. You can maybe come up with what you're multiplying by next to get there, but the fact is it's not a common ratio either. This is a case of neither. And if a teacher, or if a test or question asks you to show work on it, justify your answer, this is your justification. Yes, I can tell by appearance, and I use the decimal form of it, that it had neither there, but this is the actual thing that you would do to make a test like that. Anyway, they still want us to come up with a rule, and the rule isn't going to be much different from what we did in the previous set, where you have a sub n equals, there's a constant 1 on top. That's unchanging, and if the first term has a 2, the second term has a 3, it's 1 more than the one before it. That's neither arithmetic nor geometric, but it is the rule. So here's the rule we're going to use, and then let's find the ninth term from that. A sub 9 equals 1 over 9 plus 1, which is 10. Now, was there any doubt that that would have been the value? We had 1/2, 1/3, 1/4, 1/5, 1/6, 1/7, 1/8, 1/9, 1/10, which is 5 after the 4. That is the 10th term. Was there any doubt? No. I got that from the rule, though. And you got the rule from the terms. All right, number 12. Alternating signs is a possible sign of a geometric sequence, and a common ratio is more of a sign of a geometric sequence. Number 12 is a common ratio of -3. We're multiplying -3 from one term to the next. This is geometric. As a geometric sequence, we can use the rule that we spoke of before. We have a first term of 1, a common ratio of -3 raised to the n-1 power. The 1 is not required. The parentheses are. As long as that's a negative there, we have to raise it to that power in that way. We want to find the ninth term of this rule. So we are going to be doing -3 to the 9 minus 1 power, or -3 to the 8th. I'll let my calculator work itself out here. And the parentheses, once again, are important. There's a difference between having -3 in parentheses for this problem and raising to the 8th power versus not. This one will be a positive number. If you don't put parentheses, it won't be a positive number, and it needs to be positive. 6561. Let me be clear. Your answer doesn't need to be positive. The ninth term needs to be positive. Because the first term is odd, the third term is odd. The first term is positive, the third term is positive. The odd terms are positive. The ninth term is an odd term. It should be positive. The even terms would be negative. But that one needs to be positive. We need to follow that up. Number 13. One term of an arithmetic sequence is a sub 12 equals 9. 19, a sub 12 equals 19. The common difference is d equals 7. Write a rule for the nth term, then graph the first 6 terms of the sequence. Okay. Common difference means it'll be arithmetic. So with the nature of this problem, we have the rule as spoken that the value of the nth term, in this case we could say the 12th term, takes the first term, which we don't know, and adds the common difference, which we do know, and adds the common difference, in this case 12 minus 1 times, 11 times. This was 12 minus 1, this was a sub 12. So we're doing a substitution of, this is n, this is a sub n, and we're plugging those in so we can find the first term, and we can write a rule with that. There's technically nothing wrong with, there are different ways we can write the rules. I could do it based off of a sub 12, but that's not what we're dealing with here. We're going to simplify what we have. I mentioned that in the section itself, in section 7.2. If you want to find more questions of that variety, go ahead and check them out. They exist somewhere in there. Subtract 77 from both sides. You'll get a sub 1 equals negative 58, if I did that right. And then that is your first term. Your first term we're going to use. And so your rule will be a sub n equals negative 58 plus 7 times n minus 1. If we simplify that now by distributing the 7, 7n minus 7 and the minus 58 is negative 65. Great, there's the rule. Now, I don't plan on doing very much with this rule. Now that I have the first term, I can use the common difference of 7 to generate the first 6 terms, which is what we need to graph. So my first term is negative 58. My second term is negative 51. My third term is negative 44. I'm literally just adding 7 to each number, which is kind of like subtracting 58 minus 7, 51 minus 7, like that. And let's graph those. Let's plot those on a graph. I'm going to use, while I'm getting kind of graph axes right here. I'm copying and pasting them, and I'm going to use just one of the small quadrants. I'm going to use the fourth quadrant because all these numbers are negative. So I'm using this guy. I gotta move these things over. Give me a second. Gotta say, not one of my more efficient and cleaner videos to date. I apologize if it seems a little sluggish. Maybe you're just like, all right, I'm with you. First term's negative. Oh, let's change the scale. Let's go by 12s is too weird. Let's just go by 10s. Negative 50, negative 100, although I have nothing to really fit in that area. So negative 58 would be around here. Negative 51, negative 44, negative 37. You can see that constant difference, negative 30 and negative 23. Those would be the first 6 terms of that sequence. Number 14. 2 terms of a geometric sequence are a sub 6 is negative 50 and a sub 9 is negative 6250. Write a rule for the nth term. This is geometric, so we have to use the geometric sequence rule. Well, you don't have to. There are other versions of this you can do. I'm going to leave it at that, though. So the 9th term being negative 6250 is going to be found by taking the first term and multiplying the common ratio n minus 1 times, in this case 9 minus 1 times, which is 8. And the 6th term of negative 50 is found by taking the first term and multiplying by the common ratio 6 minus 1 times, or 5 times. 2 ways to solve this system of equations where we need to find the first term in the common ratio. That's our goal. To write the rule, we need to find the first term in the common ratio. And in order to do this, we can solve by elimination, which means dividing these things up, which is what I actually like to do more. Or what the book likes to do more is substitution. And I'm going to honor the book in this case because maybe it's what your teacher would speak to more. So your first term can be rewritten in such a way that you can divide the r to the fifth power here. So you get negative 50 over r to the fifth. And then you can substitute this in for a sub 1 in your other equation and then write that out down here. So now this equation can say negative 6250 equals negative 50 over r to the fifth times r to the eighth. And we do this because now we're just down to one variable in one equation. R to the eighth divided by r to the fifth, fractions subtract is fractions. Exponents subtract in this case, and you get r cubed. And I will divide both sides by negative 50 here. Boom, boom, to get r cubed by itself. That 125. I think it's 125. Let me check it. 6250 divided by 50. Yeah, 125. So r cubed, and I should have known that. It's a perfect cube. R cubed is 125. When you take the cube root of both sides, you're going to get an r value of 5. And there are cases, guys, this is the quiz review, so I'm just going to bring this up because there's probably no other question like this. If I took an even root of a value, like a square root or a fourth root, you would be getting a plus or minus scenario, which could show up. That's not in this case here. It's just a positive 5 from that positive common ratio. Now, we still have to find the first term, and we can use, for example, this is not going to be a very pleasant number at all. A sub 1 is negative 50 over 5 to the fifth power. 5 to the fifth power is, I think, is 3125. So this is negative 50 over 3125. You can absolutely bet that these can reduce. You know what I'm going to do to reduce this? Because I don't know off the top of my head. I'm going to do this without a calculator. I'm going to impress somebody in the world with it, even if it's myself. What I'm going to do, negative 50 can also be written as, it's 5 times 10, and 10 is 5 times 2. So negative 50 can be written as negative 2 times 5 squared. I bring that up because 5 squared over 5 to the fifth. What did I say about exponents? What they do when the same base divides? They subtract. I can remove the 2 from here, and I can remove 2 from here, and you're left with 5 cubed. That's negative 2 over 125. Boom. That's my version of reducing that. Now, I still didn't write the formula, but that's negative 2 over 125. So the rule is a sub n is, here's the first term, here's the common ratio, and raise to the n minus 1 power. That's how geometric sequences roll. Do we have to graph this? No, just write the rule. Okay, I'm really glad. Okay, so that is number 14. Numbers 15 through 17 find the sum. This is for sections 7.2 and 7.3, so they are specifically arithmetic series and geometric series of the finite variety. I think section 7.4 is going to be on infinite geometric series, which I don't know how they're going to get in the proof of the formula. I'll be getting into it with you if they don't. That being said, we'll save that for that section. Oh, all I was going to say on that was you have to know that finite geometric series formula if you want to follow along with the proof. All right, this is clearly an arithmetic series. Now, for the arithmetic series rule, I write it slightly differently than the book does. It's the exact same calculations. It's just where I put the divided by 2. I pair off the number of terms that I have and multiply it by the sum of the first and last term because it's the same as the sum of the next two terms as you move successively inward. Goal is we need to know the number of terms, the value of the first term, and the value of the last term. The first term is 3 times 1 plus 5, which is 8. The last term is the ninth term. The last term is 3 times 9 plus 5. 27 plus 5 is 32. And the number of terms is 9. It's not always just that number. We go from 1 to 9, which is 9 total terms. So we got to use these three numbers in your formula. S sub 9, the sum of the first 9 terms. We divide 9 by 2 and multiply by the first term plus the last term. That's 4.5 times 40, which is 180, I believe. So you got a sum of 180 for those terms. Number 16 has the clear and present danger of a geometric series. Given the appearance this guy is taking on from the first term to the fifth term of 11 times negative 3 to the k minus 2 power. This one's interesting because it says minus 2. It takes on the appearance of a geometric sequence, but remember the geometric sequence rule is a minus 1 there. That's for when this thing is the first term. I'm going to give you a heads up. 11 ain't the first term. 11's actually, in this case, the, second term? 11 in this case is the second term, I believe, if I'm doing it right in my head, is the second term. We need to find the first term because by the way, the geometric series rule looks like a sub 1 times 1 minus r to the n power over 1 minus r, which means we need the value of the first term, the common ratio, and the number of terms. Now, the first term, this must not be that's a k. I'm like, this must not be an I if that has a k right there. The value of the first term, we actually got to substitute 1 into there instead of just assuming it's that 11. This is 11 times negative 3 to the negative first power. Negative exponents means division, means we're dividing by negative 3 to the positive first power, so negative 11 thirds. I don't know why I didn't just write what was there, but this is the first term. Weird number, we're going to have to deal with it. The common ratio, however, is negative 3. That's what we're multiplying by each time k increases by 1. So there's a common ratio. And n is from 1 to 5. That is 5 total terms. So we got this, that. And they're going to substitute into here. Okay. Probably one of the weirder sets of values I had to work with, given that the common ratio is negative. We didn't do a lot of those. We should. But that first term, s sub 5, that's an s, that's a 5, is negative 11 thirds times 1 minus r to the n power over 1 minus r. There's a lot going on here that I got to unpack and speak about. For one, you could totally treat this 3 as multiplying with the denominator. Keep that in mind. As negative 11 or whatever can multiply with the top. Number 2, I can do 1 minus negative 3. Listen, I want to clean up what I do here instead of going straight to the calculator. That's a personal thing. You can go to the calculator, but you got to be very, very careful about your order of operations and what goes in parentheses. We'll talk about that part in a moment. Down here, I have 3 times 1 plus 3, which is 4. So there we go. Up here, I have 1 minus and then negative 3 to the 5th. Generally, I don't clean this stuff up in this way, but I do want to just get it in. Like, normally I don't write this much, but I want to try and do as much practically as I could. Oh, I knew 3 to the 5th. I don't know why I did that in the calculator. So that becomes a 1 plus as well. So negative 11 times 1 plus 243 is 244 over 12. At this point, I'm comfortable using the calculator. I don't know if this has a clean answer because the first term is a fraction. So I'm guessing it won't, but we can write a fraction answer from that. So let's do negative 11 times 244 divided by 12. And that's this number here, so it will be some sort of over 3. If we go to fraction form, you want the exact answer here. So this is negative 671 over 3. And that's what we get there. I guess it stands to reason that I could have reduced 244 over 4 and made it some value before we moved forward on that one, but that's what we'll get. There's a mixed number version of that answer, whatever it is, I guess. Well, I guess we know what it is. It's negative 223 and 2/3. I'll keep the improper fraction as long as it's reduced. I'm good. Okay, number 17. 3 more questions still. We're going from the first to the 12th term. This is yet again a geometric series, so we haven't escaped it. And once again, given that this isn't just minus 1, then this isn't the first term. It's a little trickier than that even still, but we need to find it by substituting 1 into there. So negative 4 times 1/2 to the 1 plus 3 powers to the 4th power. 1/2 to the 4th power is 1 over 16. So this becomes negative 4 over 16, which is negative 1/4. So negative 1/4 is the first term. The common ratio is 1/2, and or 0.5, and the number of terms is 12. So when it comes to this, I'm probably going to use the calculator sooner than later on it, but still a substitution is to be had. I'll try and simplify what I can. This is the sum of the first 12 terms. You take the first term in the same way. It's a fraction. It's a little weird. And you multiply by 1 minus the common ratio raised to the 12th power over 1 minus the common ratio. So negative 1 times whatever happens here. This is 1 minus, I think 2 to the 12th power, I think it's 1 over 4096. I want to try and see how much I can do without the calculator here. 1 minus 1/2 is indeed 1/2. Oh, and there's a 4 down here as well. So 4 gets to multiply with 1/2, and we know half of 4 is 2. Yeah, my work's going to be a little messy, y'all, because go to the calculator whenever you're ready. -1 is the same as making something negative, so we'll make this answer negative. And 1 is 4096 over 4096. The case in point is we're subtracting 1 from the top. This is going to be negative 4095 over 4096 on top, and on bottom we have 2. And so dividing this by 2 is the same as making this 4096 2 times larger. I believe the final answer will be negative 4095 over 8,192. I don't think that reduces, but just that right there. That was a calculator-free venture, if so. I trust my math, but that's a calculator-free venture, if so. And that's the sum of the first 12 terms of that thing. Use the calculator whenever ready on that. Be careful in order of operations. Number 18. Pieces of chalk are stacked in a pile, I guess like so. Part of the pile is shown. The bottom row has 15 pieces of chalk. The top row has 6 pieces of chalk. Each row has one less piece of chalk than the row below it. How many pieces of chalk are in the pile? So we start with, well, not start with 15, but 15 on the bottom. This continues all the way to 6. There aren't 6 in the drawing, but all the way to 6. Okay. I could write them all, but the point is I'm going to add, this is an arithmetic series. There's a common difference of -1 from one term to the next. It is a common difference, and we know our first and last term, which is great. What we need to know the number of terms. I believe it's 10, 15, 14, 13, 12, 11, 10, 9, 8, 7, 6. There are 10 terms. So what we need are the first term. I guess we don't need the common difference. We just need to know it's arithmetic. We need the first term. We need the last term. And the number of terms. 10. So in our arithmetic series rule, the sum of the first 10 terms, you pair them off and multiply by the sum of the first and last terms there. Here's the point I wanted to make. Let me put a +7 here for a second. 15 plus 6 is 21. 14 plus 7 is also 21. So it would be 13 plus 8, 12 plus 9, and 11 plus 10. All of them add to 21. There are 5 pairs total. That's where we're getting the 10 over 2 from. So we get to add all 5 pairs of 21, and we get that answer, 105. So 105 pieces of chalk is what we're getting there. Anyway, that's how the formula kind of derives. That's how I write it the way I do. And I'm not going to forget it. Okay, we have one more question in number 19. Probably a hard one. You accept a job as an environmental engineer that pays a salary of $45,000 in the first year. So A sub 1 is $45,000. After the first year, your salary increases by 3.5% per year. Okay, actually, that's not too bad. Common ratio, here's the thing. 0.035 is 3.5%, but you got to add it to 1 because you need to increase by it. If you want it to increase, you got to multiply by a number more than 1, and 1 gives you the 100% of plus an additional 3.5%. Write a rule given your salary A sub n for your nth year of employment. This is a common ratio because of multiplying increase. That's how this works. So 45,000 times 1.035 to the n minus 1 power. And you got to use n minus 1 in this case if this is your first year. By substituting 1 into here, you are going to get 45,000. This should be part A. Part B, I thought it said wait till your salary. What will your salary be during your 5th year of employment? Well, we substitute 5 in here. I will absolutely use the calculator. But don't let the calculator do 5 minus 1. You know that part's 4. Go to the calculator after that, and then let it rip. So 45,000 times 1.035 raised to the 4th power, which is that guy. So I'm going to go down to the cent. 54 cents is how I'm going to round up. $51,638.54. Give me my cents. Give me my money. What was the situation? Environmental engineer? All right. Doesn't seem like a lot. Part C. You work 10 years for the company. What are your total earnings? Justify your answer. Now this is a sum. You add the 45,000 the first year, this the 2nd, 3rd, 4th. Here's your 5th year. Add those in. The sum of those 10 years takes your first term, times 1 minus the common ratio raised to the 10th power over 1 minus your common ratio. This time, for everyone's sake, I'm going to go straight to the calculator because I need to show you how order of operations work in this situation. Notice what's written. Write it down for yourself. Press pause if you need to write it, because I'm going to go to the calculator in 3, 2, 1, go. All right, so we're going to do 45,000 times 1 minus... Actually, all this is pretty direct. The one thing that I need to be sure of is close these parentheses here. And in the denominator, if I'm going to do this in my calculator instead of just putting as negative 0.035, you've got to put that in parentheses, like so. So this will compute to the total sum. It's money, $527,912.69. Give me my money. So, $527,912. They say justify your answer. My math is justification in and of itself. There we have it. Okay. Guys, that is our quiz review. That'll do it for this one. This is Mr. Robinson. Thank you so much for watching. I like to try and think of what was missing in this set, and I can think of a few things. In the set of, let me go back really fast. In a problem like this one right here, number 14, we also did these for arithmetic sequences. So you might want to take a look when you have two terms where neither's the first term. We also did one like this for geometric sequences. We did them in section 7.3 where you have one term and the common ratio. There were word problems in the geometric series set where we were doing these like monthly payments from a loan. I don't know if those will show up on a quiz. Those are pretty tricky. There's a big formula involved, and I'm kind of glad they didn't show up here. So a lot of different things were here, but they really liked those special cases of the non-arithmetic and geometric ones. Hey, they were a bit of a challenge to talk about, but I hope we got through it just okay. Guys, that'll do it for this one. This is Mr. Robinson. Thank you so much for watching. Take care, and I'm going to see you in the next one.